The biggest surprise in space propulsion is that the bottleneck is often not the engine. It is the power system, the heat you cannot get rid of, and the testing you cannot afford to run long enough. Chemical propulsion still owns the moments that matter most. Launch, ascent, big course changes, planetary capture, landing, and crew abort all demand high thrust on demand. Those are short, intense phases where you trade propellant for certainty. That is why, even as electric systems improve, chemical engines remain the operational baseline for the riskiest minutes of a mission. Electric propulsion plays a different game. It is for long, patient maneuvers that quietly add up. Orbit raising, station keeping, cargo repositioning, and deep space cruise corrections reward efficiency over urgency. If you can keep power flowing for months, low thrust becomes high impact. That is the first strategic pattern. Propulsion is not one market. It is mission phases with different physics. Plasma propulsion is often talked about like a single category, but it is not. It is a family of approaches that happen to push on ionized propellant. Arc jets, Hall thrusters, microwave plasma concepts, pulsed plasma microthrusters, and magnetic containment ideas all live under the same umbrella. Each one brings its own constraints on stability, erosion, power processing, and scaling. Treating plasma propulsion as one thing leads teams to make the wrong comparisons too early. One of the most durable lessons is that architecture beats hardware. Hybrid approaches that combine chemical propulsion with solar-electric propulsion have been studied repeatedly across Mars missions and even Titan-class mission concepts. The core insight is simple. Sequencing matters. You can use chemical thrust for the time-critical steps, then use electric propulsion where time is available and mass savings compound. In practice, that can change total mission mass more than swapping one thruster model for another. When leaders ask which thruster wins, the better question is, which timeline wins? How long can you accept thrusting, and where can you accept it? If you can spiral outward slowly using electric propulsion, you might reduce the chemical propellant you would otherwise carry. If you need rapid capture, abort options, or tight crew time limits, you shift back toward chemical capability. Propulsion selection is not a beauty contest. It is a plan for how you move, step by step, while staying safe. That brings us to the underappreciated heart of high-power electric propulsion: power conversion and conditioning. Engineers were already treating this as a first-order constraint as far back as 1964, in analysis of 300 to 1200 kilowatt-class plasma propulsion systems. That range matters because it forces you to confront reality. Efficiency and reliability of the power processing unit become propulsion performance. If your power electronics are heavy, fragile, or waste too much energy as heat, the thruster's theoretical promise does not matter. Heat is the silent tax on electric propulsion. Every inefficiency turns into thermal load. Thermal rejection is not optional, and in vacuum it is unforgiving. Radiators add mass, add area, and complicate pointing and operations. They can also become a constraint on where you can thrust and for how long. So scaling electric propulsion is never just about better plasma acceleration. It is about an integrated powertrain, power conditioning, thermal control, and mission operations working as one system. Lifetime is the next gate, and it is where many programs stumble. Hall thrusters, a mature and widely discussed class of electric propulsion through plasmas, illustrate the point. Their mission utility is governed by available power, by wear mechanisms, and by plume interactions with the spacecraft. Erosion is not just a maintenance problem. It can be a mission-ending problem if performance degrades, if debris contaminates surfaces, or if plume interactions create unexpected forces and charging effects. For fleet-scale adoption, endurance evidence and contamination budgeting matter as much as any performance claim. Plume interaction is also becoming a coordination problem, not only an engineering problem. As orbital environments get denser, the externalities of propulsion become more important. Exhaust plumes can affect sensors, optics, and nearby vehicles. That pushes the industry toward shared standards for contamination budgets, telemetry, and qualification regimes. In other words, propulsion maturity is partly a governance and interfaces story. A thruster that cannot be integrated cleanly becomes a niche tool, even if it performs well in isolation. Diagnostics deserve more respect than they usually get. Microwave plasma diagnostic methods have been treated as a development requirement, not just a lab accessory. That is a subtle but profound shift. If you cannot measure what the plasma is doing, you cannot validate models. If you cannot validate models, you cannot certify lifetime. If you cannot certify lifetime, you cannot commit mission architecture to it. For long-duration propulsion, the test stand and the diagnostic suite can be as strategic as the thruster itself. Small thrusters, especially pulsed plasma microthrusters, point to a different kind of compounding. Back in 1982, microthrusters were framed as a coherent development line, not a curiosity. That framing looks even more relevant as spacecraft shrink and proliferate. When you have constellations, inspection vehicles, distributed sensor networks, and formation flying, tiny impulse bits become valuable. A small maneuver, repeated thousands of times, can become an operational capability, like precision station keeping, rendezvous, or delicate proximity operations for servicing. Advanced magnetic or contained plasma concepts sit in a more speculative zone. The literature includes proposals where magnetic containment becomes a variable in the propulsion architecture. The promise is compelling, but the gates are tough. Stability, efficiency, lifetime, and power processing requirements must be met before such concepts graduate from intriguing to fundable at scale. A useful discipline is to treat them like any other system, with hard go or no-go criteria, not as exceptions that live on optimism. Another enduring lesson comes from mission comparisons that put chemical propulsion, nuclear thermal, and multi-megawatt electric propulsion side by side, such as a 1991 Mars-focused comparison. The takeaway is not that one option wins forever. The takeaway is that assumptions must be exposed. Power system maturity, payload margins, transit time tolerance, crew exposure, abort modes, and logistics shape the true answer. If those assumptions are hidden, the comparison is not analysis. It is advocacy. For planning through 2050, a realistic picture is mixed. Chemical propulsion dominates launch and other high-thrust phases. Electric and plasma systems expand in satellites, cargo transfer, orbit raising, and precision maneuvering. Hybrid chemical plus solar-electric designs become a standard option when schedule allows. The compounding effect shows up in logistics, not hero burns. Cargo moved efficiently enables staging, refueling, servicing, and a more routine cadence of missions. From 2050 to 2100, the opportunity is to make cislunar and Mars logistics less bespoke. Higher power electric propulsion, hybrid staging, orbital refueling, and in-space servicing can turn exploration into transportation. But only if the enabling stack matures together. Power conditioning, thermal rejection, lifetime qualification, and infrastructure for long-duration testing are the real gates. Funding only the thruster risks building a sports car engine with no fuel system, no radiator, and no endurance testing. That has direct implications for capital allocation. The best investments may not look like propulsion at first glance. Test stands that can run for long durations, diagnostics that reduce uncertainty, power processing units that are efficient, reliable, and modular, thermal management hardware that makes sustained operation possible. These are the elements that turn repeated missions from one-off demonstrations into an industrial capability. Procurement also needs a sharper distinction between performance demonstrated and lifetime qualified. Peak numbers are seductive and sometimes irrelevant. Many mission risks live in erosion, plume contamination, restart reliability, and power conditioning failures. When a program optimizes delta V on paper while ignoring abort options or operational tempo, it creates a fragile architecture. Robust mission design treats propulsion, power, thermal control, and timeline as one coupled decision. Industrial strategy follows naturally. You want resilient capability across both chemical and electric supply chains. Chemical propulsion underwrites abort critical phases and rapid maneuvering. Electric propulsion compounds over time through logistics and station keeping. Losing either side narrows your mission design space and forces expensive workarounds later. So when you look at a new propulsion proposal, try a different filter. Ask whether the team is truly co-optimizing payload, power, propulsion, thermal rejection, and mission timeline from the first trade study. Ask what is missing in the test and qualification path, especially for long-duration operation. Ask whether the budget is buying a slightly better thruster or buying the infrastructure that makes many future thrusters usable. The memorable line is simple. In space propulsion, the winner is rarely the engine alone. It is the integrated power, heat, lifetime, and mission architecture that lets the engine matter.